Okay, I'm going to get started. Welcome everybody to EurekaFest. I'm Michael Cima, the faculty director of the Lemelson-MIT program, and I'm very happy you could join us today. Today is the first official day of EurekaFest, and this session is all about illustrating the power of invention. We will start with a guest speaker, an amazing inventor from MIT, whom I'll introduce in a moment. Today is especially exciting for all of us at the Lemelson-MIT program because it's when we all get to meet our young inventors. The 2021 high school invent teams and the collegiate student prize winners are all here today. As an inventor myself, I'm particularly interested in learning about their invention process. Normally, we would be all together on the MIT campus and we would have a big showcase where you'd have the opportunity to meet everybody that's attending in person and see demonstrations of their amazing inventions. Well, obviously we can't do exactly that this year. So the next best thing, while most of us are still working or learning from home, is to let them take the center stage online and introduce you to what they've been working on. So we have 4 separate Zoom sessions set up to start around 12:50 Eastern time. And each session will feature a mix of invent teams and student prize winners. That's our collegiate student prize winners. We're very pleased to have the Lemelson-MIT program master teachers join us as they do every year to MC the invention presentations. Our master teachers have run invent teams themselves and are true masters of the invention education process. We'll start those sessions in about 45 minutes, but first I'd like to introduce you to today's special guest. Asegun Henry is an associate professor in the Department of Mechanical Engineering at MIT. He's a colleague of mine. And he directs the Atomic Simulation and Energy Research Group. Prior to MIT, he was an assistant professor at the Woodruff School of Mechanical Engineering at Georgia Tech. And that was from, I think that's, I don't have the wrong dates here, but he was at Georgia Tech before this. He holds a BS degree in mechanical engineering from Florida A&M University, as well as a master's and PhD in mechanical engineering from MIT. So he's certainly no stranger to MIT. Professor Henry's primary research is in heat transfer, with an emphasis on understanding the science of energy transport, storage, conversion at the atomic level, along with the development of new industrial scale energy technologies to mitigate climate change. So what I think is really interesting about Professor Henry's work is it goes from the atomic scale to large industrial scale. And it's that kind of scientific insight that he can bridge the huge scales that are involved there. So we're thrilled to have Professor Henry join us today to talk about his journey as an inventor. Welcome.
Thanks, Michael. Can you all see my screen okay? All right. So thanks for this opportunity to speak. This is very befitting. I became a professor really to be an inventor. That is what I love and what I've always been into as a kid. Growing up, I was someone that always had lots of ideas. And I guess if I had to try to underscore the main take-home message of what it is I'm going to talk about today, which I'll just briefly review the technologies that we've been working on in my group. But the main thing that I want to emphasize for all of you all listening and watching is to hopefully really inspire you to never stop questioning. Things may be told to you as though they are fact, as though they are, what's possible is, this range of things and here's what's feasible, but never stop questioning if that's true, if it's possible to do other things, new things. All of the things that I have worked on inventing were all born out of um, questioning the limitations that people put before us. And in doing so, we have discovered new opportunities to do things that people didn't think were possible. And that is where the boundaries of what's possible um, can move. So there are two main technologies that we are developing in my group. I'm going to talk about both of them. I'll explain to you how they work, and then I'll be happy to answer any questions after. The first is what we call TEGS MPV, or thermal energy grid storage using multi-junction photovoltaics. It's garnered a moniker in the news media called Sun in a Box. You'll see why in a second. Um, but basically, the problem that this system of components attempts to solve is one of the most important problems that we have with regards to climate change. So I'll assume many of you are familiar with the notion of climate change, that we've done lots of damage to our atmosphere and changing its composition in a way that will not allow um, lots of species to continue existing on the earth if we don't change. And so one of the most important things we have to do is we have to do a complete overhaul of the entire power grid, the entire power infrastructure. Right now it's predominantly fueled by fossil fuels. We'd like to switch to renewables, but it's not as simple as just putting up a bunch of solar panels and wind turbines. And the reason is that the way we use electricity is not directly compatible with solar energy and wind energy, in the sense that when with the way photovoltaics or solar panels work is you only get electricity if the sun is out. So if clouds go by, or if it happens to be a cloudy day, or if you're talking about at night, then you don't get any electricity from solar panels. The similar thing with wind. If the wind's not blowing, you don't get any electricity. And so the problem is that when people want to use electricity, and the way the power grid is structured, you have to have a perfect matching between supply and demand. So if people want electricity, you have to turn the fuel consumption of the turbines up to supply more electricity. And the way the grid works now is people try to predict how much electricity people are going to use in the next 10 minutes. And they're constantly dispatching the turbines to ramp up and ramp down to meet the load. You can't do that with solar and wind. And so there's a need to try and develop some kind of battery or something that can hold electricity in between as a buffer. Now the problem is there aren't any big batteries on the grid right now. The most we have is what's called pumped hydroelectric power, and that's a great resource, except that it's geographically limited, so it only works really in the places where you have like a natural geological formation that allows you to have a high a water pool at a very high elevation. And so what we've been working on, and what I would say there's really an international race going on to try and develop an energy storage technology that's low cost. So even that pumped hydroelectric power is actually not low cost enough to actually meet the needs to actually fully decarbonize the grid and switch fully to solar and wind. And so what we're developing is a battery technology. We call it a thermal battery. Basically what it does is it takes in electricity, excess electricity. It doesn't really care where it came from. So generally we're interested in solar and wind, but it could come from other power plants as well. And what you do with that electricity is you run resistive heaters. So this is just like a light bulb. So think of a incandescent light bulb that gets glowing white hot, and you're using electricity to generate light. And most of the light you're generating in a light bulb is infrared light, and you can't actually see it, but some of it actually is visible. And so the idea here is we're using that electricity to generate light, which is a form of heat, and that heats up another medium, which is a liquid metal that we pump through this piping here. And this liquid metal gets heated up to a temperature of about 2400 degrees Celsius, which is similar to a light bulb filament temperature. And then that liquid metal is pumped over to these giant graphite blocks. These blocks are so large, this whole bank of blocks is probably about the size of half of a football field. And so it's very large, and in it being very large, it's able to store energy for very long periods of time without cooling down. And so what you do is you heat up the blocks with the electricity that came in, and you store the energy as heat rather than storing it as electricity or in an electrochemical reaction. Now, the reason this is useful is because storing heat is way cheaper than storing electricity. So that's the main advantage of this whole invention, is the fact that this is so low cost, and I'll talk about the cost in a few minutes. The idea is this is how you charge the system. When you have excess electricity you store, you pump the liquid metal through and you heat up the graphite blocks to the highest temperature, 2400 degrees C. Then it's charged up, and then when you want electricity back, which can be at any time, you pump the liquid metal through again, and you have it carried over to this power conversion module, where we convert the heat back to electricity. And this is where we pay a big efficiency penalty, but it turns out that this actually is cost effective because the cost of storing the energy is so low. Now, what's interesting here is the way we do the conversion of heat back to electricity is very different than normal. Usually what people would do here, especially mechanical engineers, is they would use a turbine. And turbines are how most power is generated throughout the world today. They're efficient and they're cost effective. But we can actually get to lower cost doing it a different way. Because we made the temperature so hot, we can actually convert the light coming off of these pipes instead of trying to use moving parts and have a turbine. And this is actually cheaper. And so these are specially designed photovoltaic cells. They're not your normal solar cell. These are different kinds of cells, but they are just like solar cells in the sense that they take light in and they give you electricity out. Now, these cells are water cooled, and they also have mirrors on the back. And the mirror is very critical because the mirror helps to keep any of the light that you don't convert, and it sends it right back to this hot infrastructure so that it stays hot and you preserve all the energy that you're not going to convert. And this is what helps make it more efficient. Now, one of the cool things about this is you can actually imagine this cooling block that keeps the cells cold being retracted. So you can actually actuate it in and out of the light. You have this like little unit cell where you can dip the cells in and out of the light. And what this allows you to do is give a very fast response to the grid. So if you've got solar energy, if you ever watch the output of solar energy or wind, if a cloud goes by for a couple minutes, you might have a dip in the amount of electricity output. Something like this would be able to respond very quickly by dipping the cells into the light, getting lots of power output, and changing and compensating for the output of renewables to keep a very constant supply to the grid to always meet the demand. And so this is kind of ideal from a grid operator standpoint because it's the ability to respond on the second level rather than minutes or hours, which is typical for turbines. So this is a technology we're very excited about. And if you were a mechanical engineer, the very first question you would ask or you would say is, how are you going to pump that liquid metal? Because generally pumps that operate at these extremely high temperatures don't exist. And so this was the real first invention that opened up the floodgates for lots of new things to think about. And so what we did is we questioned if you could make a pump that operates this hot. And there's a good reason why pumps don't operate this hot, and it's because of the seals. Usually when you make a pump, the seals are made out of polymers. Polymers are generally limited to temperatures around about 400 degrees Celsius. And so it's really difficult to make a mechanical pump that would operate at much higher temperatures. And so what we did is we found a new sealing material and new ways to make seals. And so we can make an entire system out of graphite and ceramics. This is, in this particular instance, this was aluminum nitride. We actually made a pump out of a ceramic. It was a gear pump. And what you're seeing here on the right is a video of the very first time we pumped at 1350C. We cut a hole in the insulation so you could watch the liquid tin flowing. By cutting a hole in it, a lot of the light gets out and it actually cools down. And so we've since then done versions where we measure the flow rate and we've actually pumped above 2000 degrees Celsius. So there isn't really much of an intrinsic limit other than the boiling point of the liquid and the strength of the materials, but ceramics and graphite can remain strong above 2000 degrees Celsius. Now, another key piece of this technology, and this is more recent, this is new stuff as of the last couple of months. The other key piece that I mentioned is the photovoltaic cells. Those cells are also referred to as TPV or thermal photovoltaic cells. So they're like infrared photovoltaic cells. And for the last about 40 years or so, the record for thermal photovoltaic efficiency was about 29%. Last year, someone pushed it up to about 32%, but it's never gotten above the average efficiency for a turbine. And so thermal photovoltaics has never really been considered a really top contending technology for power generation. And recently we just set a record and pushed it up by 10 points up to 42%. So this is a big breakthrough in the sense that now thermal photovoltaics will be in the discussion for how you generate power in lots of applications, and it's a really key step on the way to 50%, which is our goal for our energy storage technology. So what's shown on the right here, this shows the reflectivity of that mirror I mentioned that's on the back of the cells. Our reflectivity on these cells was not the focus of this initial effort. We were trying to make really good cells, so the reflectivity is down at between 92 and 93 or so percent. If we push the reflectivity up to about 97 or 98% for these cells, we should get to about 50% efficiency, which is our goal. So that's our next push. That's the next thing we want to do. And cells, this 32% here, just to show that the high reflectivity is possible. How they got to this 32% was they got to above 98% reflectivity. So above 98 is actually possible, and we think we can get to this goal. So this is another big invention that was done through collaboration. Now, here's the last piece I want to mention with this in terms of the cost. So the cost is really low. So this shows, all the various costs that go into all the components that scale with the energy. And here's the components that scale with the power. Just to give you a sense, this shows $10 per kilowatt hour. The cost of lithium-ion batteries is over $150 a kilowatt hour. So we're talking about 10 times cheaper than batteries. And so that's why this is so exciting and compelling, despite the fact that it's much lower efficiency than a battery. And that's all included in this analysis. In addition to that, if you compare it to a turbine, the cost of a turbine is up around $1 a watt, and we're down closer to 35 cents, or we actually have approaches that can get down to less than 25 cents a watt. And so this is where another big gain is here. And so it all comes from the fact that the cost of the storage medium is really simple. We're just using graphite, and it's very cheap. And so it's the fact that we have a cheap material. The last thing I want to talk about is a completely different technology. So this is the second technology we're developing in my lab. Here, the problem we're trying to solve is hydrogen. So hydrogen today is made for the purpose primarily of for petrochemicals and also to make ammonia. You need ammonia to make fertilizer so that you can grow food, so you can feed 7.5 billion people on this planet. So hydrogen already plays a very essential role in our way of life. And the way that we make hydrogen today involves taking methane or natural gas and reacting it with water. And in doing so, you end up making CO2. It's like required that you make the CO2 in order to get the hydrogen. What we're trying to do is take advantage of the fact that we can now operate systems at extremely high temperatures to now get rid of the CO2 and instead take methane, heat it up so hot that it actually falls apart. So if you heat it up in the absence of oxygen, the molecule itself becomes unstable, and you'll actually get solid carbon and gaseous hydrogen. And so we are actually not the original people that came up with this concept of doing it with liquid tin, but I'll show you where our new invention and where our new contributions are. So if you do this reaction, the problem with this reaction is that you make a solid byproduct. So the simplest thing you can imagine doing is, okay, just make a tube, I heat it up to, this reaction comes to completion around 1400 degrees C. You heat it up to 1400 degrees C, the reaction will happen, you'll get hydrogen coming out the other end of the tube, but the problem is that solid carbon is going to deposit on the inner walls of that tube. And very quickly, you're going to block the entire cross section, and your entire tube will be plugged with carbon, and you won't be able to use your reactor anymore. You have to shut it down, get a plunger, plunge out all the carbon, and then heat it back up, and that's a very inefficient process that's not very cost effective to do. So what we want to do is make a continuous reactor, and so there was a group in Germany that came up with an idea of taking liquid tin as an inert liquid, because tin actually does not react with carbon and it doesn't react with hydrogen. So it's inert, so it doesn't chemically react with anything in here, but you can use it as a means of transferring the heat to the gas so that you can carry out the reaction and keep the carbon from sticking to anything. And so the idea is you start with a big container of liquid tin, you bubble up methane, the reaction happens now inside the bubble, and when the bubble reaches the top, you get a little carbon particle that floats on the tin surface and the hydrogen goes out. Now, the other groups that have looked at this have not been able to get to 1400 C. They haven't been able to show a continuous reactor because they've made their reactors out of steel, which gets eaten alive by liquid tin. And so instead, what we do is we use our ceramic and graphite infrastructure to now be able to operate at the peak temperatures necessary to complete the reaction. And we can pump liquid tin, so we can move the carbon out by floating it on tin and carry it out of the reactor in a continuous manner. And we can also do very clever approaches to heat exchange, where we preserve the heat in the hydrogen and the carbon and recycle it so that we can make a very efficient reactor that's cost effective. So with that, I'll stop here and take any questions, but these are the two technologies that we're working on in our lab.
Thanks, Asegun. That was really great. You know, your comments early on about not accepting something, being told something is impossible, is reminds me of something I learned a long time ago about great science and great engineering. And what are those things? Well, great science is at the boundary of what's known and what's unknown. But great engineering is at the boundary of what's thought possible and what's thought impossible.
Exactly.
And the kind of work you're doing is a great example of that. So I think Betsy is going to take questions and give them to you. I think she's screening them right now.
Sounds good.
Okay, we have a handful of questions for you. So I think you touched on this, but somebody's wondering why you chose tin over other metal possibilities.
That's a great question. There's a lot that goes into that choice, actually. So there are a couple of reasons for choosing tin. Tin, for the major issue is that tin actually does not react with carbon. So that allows us to make an entirely graphite infrastructure made out of carbon, and we have no corrosion whatsoever in our system. And that's key, because what we did is we basically, if you talk about high temperature materials, high temperature systems, corrosion is the number one topic always in discussion. And generally that's because most reactions and solubilities change with temperature. And so what happens is things react much faster as they get hot. And so as you go really hot, all kinds of things transform and change very quickly on you. So to be in a situation where all of our materials are thermodynamically stable with respect to each other, it allows us to operate without this worry of corrosion. And we solved that problem from the beginning. And we said, okay, we're going to use materials that we know work together. And then the hard part now is figuring out how to make these materials into the system we want, which is the harder problem we went and solved. So we mainly choose tin because of its lack of reactivity. It also does not oxidize very exothermically, so it's not like it's going to explode like the alkali metals. So things like sodium and potassium have been used in nuclear contexts, and those materials tend to react very violently with water and oxygen. Tin does not. The last component for tin is actually tin is cheaper than other options such as like gallium. Gallium's nice because gallium actually melts right near room temperature. Tin melts like solder above right around 200 degrees C, 232 C. And so the lower cost of tin is really the reason we went with tin instead of gallium. Gallium is about a factor of 10 or more expensive than tin. And so tin's mass produced for solders and other applications. And so it's a good choice kind of all around. It's a good compromise.
Great. So now we have a question from one of our collegiate student prize winners. She says, thanks, Professor Henry, for your awesome presentation. You mentioned how your impressive research results came from collaboration. Can you share more about collaboration in research?
Yeah, collaboration is key. I mean, at the end of the day, we have one particular piece of expertise and we like to think about full systems, but we don't do everything and you can't do everything. So in the case that I was showing, the photovoltaic cells that we made that were record high performing, let me actually show that slide again if I can, so you can see it. This slide here. These cells were actually made by collaborators at the National Renewable Energy Lab. So these are literally some of the best cell makers on the planet. If you go look up the highest performing solar cells ever made, this is the group that did it. So we went and found the best people on earth to make solar cells and asked them to make the specific cells that we needed for this application. And I'm really excited that we were able to get them to work with us, and they did an amazing job. And you can see, bringing them with all that experience in optimizing for a different application for direct solar conversion, bringing them over to this new application they did this in 2 years. In 2.5 years, they were able to take the record from 32% up to 42%. And so this is the power of collaboration. Instead of trying to do it ourselves, we went to who's the best.
That's great. We have a couple of questions in the same vein. Basically, people want to know, when will this be ready for home use, or will it be ready? Is it scalable for residential?
So it's definitely not scalable down for residential purposes. Part of how this works and what makes it work well is that it needs to be large. So you can think of it this way. There's a particular quantity you compute for a system like this, which is called the surface area to volume ratio. So when you make something small, the amount of surface area it has, if you take that and you divide by the total volume inside, you will get a much larger ratio when something is small. But when something becomes huge, it's predominantly volume and much less surface area. And so what happens in this case is that for heat transfer, the rate at which you're losing heat to the environment, because you got something hot inside of a box, you're always going to be losing heat to the environment. You can't stop it. The rate at which that happens is proportional to the surface area. Now, the amount of energy you have stored inside is proportional to the volume. So when you make it huge, you have so much energy stored inside that a very tiny fraction of it is what's leaking out throughout the day. When you make it small, take for example a cup of coffee. If you put something as small as a cup of coffee on a desk, it starts out hot, but very quickly it cools down. And so the time frame in which it cools for a cup of coffee is on the order of an hour. For a large, ginormous, let's call it, I guess, a tank or reservoir of thermal energy like we're talking about, the time it would take to cool down is on the order of months. So it's so huge, it would take months to cool down.
Okay. Somebody is curious about who your biggest influences were in becoming an inventor, whether it was back in grade school, high school, in getting one of your degrees.
Two people come to mind. The first is, I guess, an ancient one, which is Imhotep. Imhotep is considered the world's first multi-genius. He lived in ancient Egypt many, many years ago, and I was always inspired by the idea that somebody Black in particular that lived many thousands of years ago was considered such an amazing genius. That's his legacy is apparently where the Hippocratic Oath came from, and he was actually revered as a god in Greece because he was so smart. So he's, I guess, my first inspiration. I would say second, more tangible inspiration, people that I met, particularly was my mentor, Dr. Makola Abdullah. He was a professor at Florida A&M before I became a student there, and when I was a student there. And he's gone on now. He's a university president. He's the president of Virginia State University now. And for me, what it was he really instilled the confidence within me. He was the first person to really tell me, I think you got what it takes, and I want you to work with me, and I'll pay you for a summer to do research on whatever it is you want to do. And he let me pick the project. He gave me the freedom to think about whatever I wanted to invent. I remember I invented something that summer. And I think someone taking that kind of leap of faith on me and giving me that much freedom is what got me kind of, I guess, addicted to the idea of being free to work on whatever I want, which is what guided me to being a professor, because I really wanted the freedom. I love working on the stuff that I care about in that period of time and not having to be told what to work on.
Okay, we have a couple questions about your inventions, the ones you've been talking about today. When you expect those to reach the market, how far away are you from that?
It's a good question. So part of this depends on money. So right now, where we are development-wise, we've got cells There's some more improvements to do with them, but we've got something that's very compelling already with the cells that would be profitable. We've got the pumping, we've got the whole infrastructure. And so I would say within the next 12 months or so, we're planning to try and demonstrate a full laboratory scale prototype that actually has energy storage and can be charged and discharged repeatedly and generates some power or converts power. And within 12 to 24 months after that, depending upon if we can raise the funds quickly enough, we'd like to do a pilot. So much larger. So what we are going to build in the lab is going to be on the order of what we call 10 kilowatt hours of electricity stored. The pilot we're envisioning is order 1 megawatt hour, so about 100 times bigger. And then if that's successful, we would like to then go up to 50 to 100 megawatt hour to a gigawatt hour. So hopefully within 4 to 5 years, you'll be hearing about this being, commercialized with first real commercial demonstrations.
All right, everybody, keep your eyes out for news on that. I think we have time for one more question, and we got a good one. I think a great way to close this out, which is, what advice do you have for young inventors?
Well, there is two things. There is a path, and generally speaking, if you're an inventor and you have great ideas in your mind, there are a couple things that have to come together for you to bring them to reality. One is the resources you need. Generally speaking, some of the greatest inventions may happen under different circumstances, but lots of inventions do happen in laboratories or in some kind of setting where you have resources and people to come together and work on something. And how you put yourself in a position to have access to those resources at this point, if you're at high school age, is to go to school and do well in school. I think that's by far one of the biggest keys that you can give yourself to being able to have access to teams of people, groups of people, funding, and things that will ultimately distinguish you and get you access to the resources you need to run with your ideas. At the end of the day, great ideas will flourish. The world has problems, and if you've got a great idea for how to solve it, people will come together to try and make that happen. One of the things you'll want to do is to, like I said, make sure you do well in school. That also can open up pathways for you to not have to pay for school. So try to get scholarships and things like that. But, once you get some credentials behind you and people know that you understand not just your invention, but many other things as well, so that you can properly compare your invention to other incumbent technologies or incumbent ideas so that you can understand the full scope, then that is what will give people a lot of confidence in investing in you and your ideas. And so I would say, the other thing I would say is, and this I struggle with myself, I always feel like the last great idea I had is the last one I'll ever get, but try to have some confidence. If you come up with lots of good ideas, you will likely have more. You will likely have more great ideas as you keep going. And so, if you've got a great idea, be willing to and have the courage to invest in it yourself. Take the time and the energy to invest in it and treat it as though it's your baby, the thing that you want to go the distance. At the same time, if there's failure, don't give up. Start again. You'll have other ideas, and you never know which one will hit.
Well, let's thank Professor Henry again. That was really fantastic.
Yeah, thank you for having me.